I'm going to talk about moment inertia, which is the measure of an object's resistance to changes in its rotational rate.
Okay, today we are talking about moment of inertia, which is the measure of an object's resistance to changes in its rotational rate. This helps us determine the relationship between angular velocity and angular momentum. Also, it helps us determine the relation between torque and angular acceleration. If one were to do an advanced analysis, it can lead to the mechanics of a complicated system, like a gyroscope, which is an example of that would be like a top spinning. So this is how you can approach a moment of inertia problem. See this is a rod, this rectangle here. And you have a shaded portion dx and then a length of L, and you have a mass which is m. And the moment of inertia equation, or the variable for moment of inertia is I. The equation is the integral of r squared dm. And to make it easier for yourself, you can have r equal x. And then so you plug that in, you have I equals integral from 0 to L, the 0 being the beginning of the rod, and the L being the length of the rod, whatever that would be in the case. And you have the x plugged in for the r, so x squared dm. So we have the shaded element dx, and it has a mass dm equal to the mass per unit length multiplied by dx. And that turns into dm equals m over L dx. So all that in the entirety, you get I equals the integral from 0 to L x squared m over L dx, which is a familiar form, and then you can go on to do a problem with that. Okay, now we're going to do an example. We want to find the MOI, or the moment of inertia, about the end of the rod. So here we have our rod, so it's right on the y-axis, so we're going to start at 0, and it's going to go to L, the end of the rod. So we're going to use the equation we used before, I equals integral from 0 to L, 0 being the beginning of the rod, and L being the end of the rod, of x squared m over L dx. And since the mass and the length are not changing on this rod, we can safely take that out of the integral and putting it in front because it is a constant. So now we get I equals m over L times integral 0 to L x squared dx. And now we can integrate it just like a normal equation. So we get I equals m of L times the quantity of x cubed over 3 from 0 to L. And when you plug those in, you're going to get the 0, you're going to get L cubed over 3 minus 0, so the 0 doesn't matter. And then when you simplify that down, you're left with 1/3 mL squared, which is the solution to this problem. Sounds pretty simple, right? So now we're going to do an example that is pretty similar to the last one with a little different twist to it. So we're going to find the moment of inertia again, but this time we're going to do it about a point 20% of the length of the rod. See, notice here that the y-axis is not against the edge of the rod like it previously was. It is supposed to be 20%, that's supposed to be 20% of the rod, so it's 20% in the middle of the rod. So now we basically do the same thing as last time. The equation still stays the same, though the limits change. So we still have I equals whatever your limits are of x squared m over L dx. But this time the limits to compensate for the 20% is where we want to find it, and then the rest 80% we will have negative L over 5. We're going to start the integral there, and we are going to end it at 4L over 5, right there. And then we calculate it the same as the last one, just with different limits. So since again the mass and the length is constant, we can safely take it out to make our lives easier. So you get I equals m over L times integral of negative L over 5 to 4L over 5, and which is the same as x squared dx that we had before. And again, you can integrate it just like a regular function that we have done before. So you get I equals m over L, and then this is what we integrated, so it would be x cubed over 3 from negative L over 5 to 4L over 5. When you get all done canceling and having fun with the algebra there, we will end up with 13 over 75 mL squared, which again is the solution to this problem. Not much different from the last one, but shows you a different twist to it.
Hello, and today we'll be talking about waves. Now, what's so important about a wave? Usually when people think of a wave, they think about a wave in a beach or like a wave in the pond. But there's more to a wave than meets the eye. Most people, when they think about waves, they refer to physics. But you can also explain waves by using calculus. Now, let's see how. So, the movement of a wave can be described for this equation. Looks simple? Not really. I'll do my best to explain this. So, this letter here, the upside down triangle, is called del, which represents the vector differential equation. So, and essentially, this equation is talking about vector calculus. Now, E stands for pressure, displacement, magnetic fields, anything that has to involve the wave, such as mechanical waves, electromagnetic waves. C stands for velocity, or phase velocity, anything that has to relate to the problem of the wave. Now, this backward 6 is a partial derivative, kind of like your d in the dx or your dy. Now, let's go a little bit deeper, shall we? So, we were talking about del. But what does del actually represent? Del, in its essence, is equal to this equation. Well, that might look a little bit confusing too. So what people usually do is they take del and they take square root, which is equal to the summation of this equation. Now this equation is how we plug it into how we describe the motion of a wave. And now the second important part of the wave function is E. Now we said E stands for displacement and magnetic fields and such, but E also has its own equation. Now E stands for this. Now, this may seem like a whole bunch of variables, but if you break it down, it's quite simple. A and B are your constants. They could be arbitrary, and you'll see why later. F and G are also functions, and they could be any function you want. And most likely, it would be a part of sine and cosine, and you'll see why later too. Basically, this equation is really essential to how a wave is described. Because E can be any function that you want. Because A, F, B, and G are all interchangeable and you can put almost anything in there. Now, why is that important? A, F, B, and G are just one part of this function. Now, imagine if you had infinitely many of E's. Now, doesn't this look a little bit familiar? This would be similar to kind of like this, right? If you take the sum of all these functions and you add it up together, you would get the values of a known function. And this function is used in our everyday life, considering that we listen to it every day. Music is essentially written by adding all these functions together, all these wave functions described here. If you add them all together, then they describe the functions of a MP3 or a WAV file. It is essential to our everyday life because, here, let me draw it for you. So let's say our wave was described to be just like this. Kind of like what Mr. Bogart said. So this looks similar to what we learned about in Taylor series, where if you take the values of kind of like the sine wave, we could break it up into a Taylor series or something. Now, the human ear, we could only hear about here, a certain amount. And this is basically what your MP3 is, and basically what a wave is. This is important because calculus doesn't only apply to physics or anything else that you might think has to relate to math. Physics is in our everyday life, such as music, waves, electromagnetic stuff. Physics and calculus are used everywhere.
Or looks better.
Oh,
I'm Daniel, and this is my colleague.
Devin. Hi. Today we're going to be talking about momentum and its applications. More specifically later, impulse. Now, the momentum principle can be used during long time interval only if the net force is the average net force during that time interval. Now, as long as we use very small intervals, the momentum principle is exactly correct for an instantaneous net force. So, let's set the limit as delta t approaches 0. We get F net equals dp, which is the derivative of momentum, p, which equals mass times velocity. Now we take dp and we divide it by dt, which equals the derivative of t time. Now, moving on to impulse, which is represented by F net delta t, which also equals delta p. Daniel.
Impulse is the change of momentum to an object of which a force is applied. Now, the impulse momentum theorem, which we have up on the board, is where delta p is the change of momentum from time t1 to time t2. t1 in this example is a, and t2 is b.
So, to begin the equation, we start with f of delta t. This equals the integral from a to b of f of dt. Now, from our earlier equation, we know that f equals dp over dt. So plugging that in, we get the integral from a to b of dp over dt times dt. Now we can cross out the dt's to simplify the equation, giving us the integral from a to b of dp, which equals delta p. So the integral from a to b of f of dt equals the integral from a to b of dp, integral of this equaling delta p.
Which brings us all the way back to the original impulse equation. Now, technically, impulse is a physical quantity, not an event or force. This type of impulse that we have in this example is idealized so that the change in momentum produced by the force happens with no change in time. This is an example of step change, like Euler's method. But it is not physically possible. This is useful for computing collision effects, such as hitting a baseball. The acceleration of a car. And now our example. A variable force, F, acts on an object of mass m that is initially at rest for a time interval t. A. Find an expression for the final velocity by calculating the impulse and relating it to the momentum. In order to do this problem, it is essential to use the impulse momentum theorem. Now, this impulse momentum theorem is equal to the final momentum minus the initial momentum. Now, since the mass is initially not moving, we can cancel out the initial momentum, therefore making only momentum of final left. Now, since momentum equals the mass times the final velocity, we can have the integral of 0 to t of f dt equal to m of the times the final velocity. In order to find the final velocity, we can easily divide m to the other side, therefore making the final velocity equal to 1 over m times the integral of 0 to t f dt. Now part B is very similar, in which we have to calculate the final velocity. But instead this time, we have to use Newton's second law, which is force equals mass times acceleration. Another way to write this is acceleration equaling force over mass. Now another way to write acceleration is by delta v. Delta v is essentially the final velocity minus the initial velocity. But since the mass is at rest, we can get rid of the initial velocity, therefore only leaving the final velocity. Which means another way to write final velocity is the integral of 0 to t of a dt. Now as stated before, a equals f over m, which means we can plug that in to the integral, which means we have the integral of 0 to t of f over m times dt. When we simplify this, we get final velocity equals 1 over m times the integral of 0 to t f dt, the same equation that we got from part A.
And that concludes this portion of the presentation on momentum.
So let's review what we learned today. Moment of inertia. Waves. Momentum and impulse.
Has its own formula in which this thing is falling down and I shall start over again. Sound waves, which are in MP3s or wave files, or they could be something falling down right now.
Ow!
No, sorry. Wait, that was me.
Talk about momentum.
Momentum! Is my hair good?
Yeah, it's fine.
You sure?
Yeah.